think we have a quorum. Welcome to week 11. I think we're in week 11 now. And what we're going to do tonight is continue our discussions of the fork join framework. We're going to look at a really, really interesting example that demonstrates fork join in all of its glory. But before that, let me just see if there's any questions about programming assignment number 3. First, I apologize for the confusions with the repo. I screwed up. This is not my year for repo management, so I apologize profusely for that. Hopefully people have figured out how to clone the new repository, and I'll be very flexible in dealing with any side effects or consequences of that, since it was really my fault. But are there any questions? All right. Well, without objection, I will share my screen and we will be on our way. Let me do a couple things here. So the example that we're going to be talking about tonight, of course, as always, is in my GitHub repository. If you go to my GitHub repository and you peek around here, you'll see something called Search Fork Join. And inside here, you'll see something called Iterative Fork Join. And we're going to be taking a look at the Iterative Fork Join example tonight. Now, as it turns out, this particular example is loosely based on an article that appears on the Oracle website. It's a bit old. It's about 10 years old at this point, but it shows some interesting features of the fork join pool. And I have the link to this in the source code that we're going to look at, so you don't have to worry about trying to copy it down. But basically what this does is it shows an interesting example of a fork join, of the fork join pool, where you're going to count the occurrences of words in a recursive hierarchy of documents in a directory structure. So we're going to look for a word, and we're going to look through a directory structure, a hierarchical recursive directory structure, to try to find that. So that's pretty much what this example is. And if you read through it, it's pretty cool. And you can learn about how fork join works and so on and so forth. What I did, of course, is I took that example and I pumped it full of anabolic steroids and made it a lot more interesting to demonstrate way, way, way more features of the fork join framework. But that's kind of where it came from originally. So this particular program, which is called the Iterative Fork Join, implements an embarrassingly parallel app that uses Java 7's fork join framework in conjunction with Java 8 sequential and/or parallel streams to search for phrases in a recursive directory folder containing the complete works of Shakespeare. And as I said, this example is loosely based on what I showed you a minute ago, but it's a lot more interesting and a lot more powerful. So probably a good place to start is by looking at the works that we're going to be searching. So if you go into the resources directory here, you'll see there's a couple of different folders or files. There's one called phrase list. And this is about, 38 famous Shakespeare phrases, cliches said by the bard, like, neither a borrower nor a lender be, or for mine own part, it was Greek to me, which is one of my favorite phrases. And just all kinds of great stuff. I'm sure if you're a fan of Shakespeare, you recognize some of these phrases, like brevity is the soul of wit. So many of these things are phrases that have found their way into modern parlance. We don't even think of them as being Shakespeare anymore. So those are the phrases. We're going to be looking for the phrases in the complete works of Shakespeare. So here's the complete works of Shakespeare. And I've organized the complete works of Shakespeare into a bunch of folders. And you can see that each of the works has its own folder. So for example, one of my favorite all-time Shakespeare plays is The Tragedy of Hamlet, Prince of Darkness. If we click on this, we'll see that there's some subfolders in there. So we have a file that basically is the title of the play, when it was written, who it was written by, obviously written by Shakespeare, a list of the cast, if you will, the dramatis persona. So that's kind of like, let's call that metadata. And then we also have another subfolder, which is all the acts of Hamlet. So here's Act 1, taking place in Elsinore, a platform before the castle. Act 2, a room in the house of Polonius. Act 3, a room in the castle. Act 4, a room in the castle, lots of rooms in the castle. Act 5, a churchyard. So each act consists of the entire text for that act. So if you look at this, you can see we've got the works, which is a directory structure that contains all the works. Then each work itself is a recursive directory structure that contains a file that's the metadata, and then a directory called acts. And then in the directory called acts is the text of each of the acts. So it's nice and recursive and so on and so forth. Okay, so kind of keep that in the back of your mind as we talk about how we're going to be searching for the phrases in this recursive directory hierarchy. So now that you know a little bit about the data that we're dealing with, let's go ahead and take a look at the main program. And this will give us a sense of what it is we're going to do. And we're going to start out by basically defining the folder where the works appear, which is called works. And we're also going to define, which is basically a string. And then we're also going to define another string, which is the file that contains the phrases for the complete works of Shakespeare that we're going to search for. So that's where the data is going to come from. And we'll talk a little bit about how we input the stuff into the program. We're also going to keep track of a list of phrases defined. Obviously, that's just going to come from reading the phrases in from the phrase list file. So we come into the main program. We're going to parse the arguments because we might want to do this in verbose mode. We might want to do this in succinct mode and so on and so forth. And then we're going to go ahead and get the phrase list. There's nothing particularly tricky or fancy here. We just open up the file containing the phrases and we convert that into a stream of strings. We filter out any empty strings and we collect the results into a list of strings. So nothing fancy at all about that. We then print out what kind of parallelism we have in the common fork join pool. This machine has 16 virtual cores, so 8 physical cores, and each core is hyper-threaded, so there's a total of 16. So the number of cores we're going to have for the fork join common pool will be 15. And then we're going to go ahead and warm up the fork join pool just to get everything up and running. And then we're going to run a whole slew of tests. And you might wonder, what the heck is going on with this, right? So we're passing in, false, 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 true, false, blah, blah, blah. And what we're doing here is we're indicating the degree of parallelism that we want to use for the searches. So are we going to be searching the works in parallel or not? Those are the works of Shakespeare. Will the different works like Hamlet, Macbeth, Julius Caesar, will they all be searched in parallel? Then within a work, are we going to search the documents in parallel? So that's another flag, true or false. Then we're going to be looking for the phrases. Are we searching for the phrases in parallel? Is each phrase going to be looked at in parallel? And then finally, we're going to decide whether we're going to take a given phrase in a given document and see if we want to search for that phrase in the document, or the act, I guess is a better way, in parallel. So there's a whole bunch of different degrees of parallelism, and there's basically 4 different variants, which could be true or false. So you all know that 2 to the 4 is 16. So we have 16 different tests we're going to run, every possible permutation of things. And when we're all done, we're going to get the results and we'll see how long everything took to run. Now, it takes a while to run the test, so I'm going to go ahead and start it up here. But then we're going to come right back to the source code and not wait for it to all finish. We'll look at it when we're done. So we have this, we're going to warm the pool up, but we're just going to kind of skip that because that's not very interesting. And now we're going to take a look here at the run test method. And that's what takes all those Booleans. So are we searching each of the acts in parallel? Are we searching for the phrases in parallel? Are we searching all the documents in parallel? Are we searching the works in parallel? Blah, blah, blah. So the first thing we do is we come up and make ourselves a string that indicates what we're doing, parallel or sequential for any given one of these parameters. And then we print that out so we know what's happening. We then go ahead and we'll basically get the root folder for the works of Shakespeare. And we decide whether we're going to do that in parallel or not. So here's get root folder. And this uses a really super cool technique, which we use to go ahead and basically search that directory hierarchy and convert it into a folder structure. And here's what a folder is. A folder is basically a data structure that can either contain subfolders or documents. So every folder has a potentially empty list of subfolders if it's got subdirectories, and it's also got a potentially empty list of documents if it has any documents in the folder at that level. And we do some fancy footwork where we initialize this stuff, and then we do some cool things. I'm not really going to talk a lot about this stuff because it relates to parallel streams as opposed to relating to the fork join pool, but it's really, really, really cool. And basically what we do is we walk through the directory structure and we essentially create an in-memory object that represents the contents of the directory. And it uses Java 8 streams features like a folder collector and filter and all this other good stuff. So that's just kind of to get everything into memory so that we can process it. What we do then is we go ahead and we create ourselves a search with fork join task. And if we go take a look for search with fork join task, you'll see this is what the search with fork join task is. And I'll talk about it in more detail in a second. But essentially, it's going to be searching a folder for phrases to find, and then it is going to decide whether it's doing the searching in parallel, looking for the phrases in parallel, looking for the documents in parallel, looking at the works in parallel. So all those things are stored as parameters. So it's going to make one of these objects. And we'll take a closer look at that object because it's very important to understand what's going on. Once we've made ourselves an object with the appropriate Boolean flag set, we're then going to go ahead and use the common fork join pool to do the processing. And that's the fun part. That's where we're going to focus our attention. So here, for various reasons, mostly having to do with the semantics of lambda expressions, we make ourselves an atomic reference, which will be parameterized by a list of search results. And then we go ahead and use our run timer time run method. I'm sure you've seen this a million times before. This is the way I automatically benchmark the time it takes to run methods, or in this case, run runnables or run suppliers or whatnot. So we start the timer, run the runnable, stop the timer, and then we put the results into the map with the name we pass in. So here what we're going to do is we're going to run the common fork join pool, use that to invoke the fork join task. The fork join task is the one we created here with the appropriate flag set. And that will kind of set the whole thing in motion. So everything will start to run. And then when we're done with that particular run, we're going to print out some diagnostics to see how many matches we found. We should always find the same number of matches for each of the different ways we run the tests. And if we're in verbose mode, then we print the results out so you can see where the matches occurred. And we run the garbage collector to get things back to a pristine state, and then go back and run the next test. Okay, so that's kind of a high-level view. And so what we're trying to do here is we're trying to do every possible permutation of parallel and sequential. Now, I'll give away a little bit of the results because it's kind of interesting to see where we're headed with this. By the time we run these things, what you're going to find here is that the stuff that's entirely sequential, right? So sequential work, sequential doc, sequential phrases, sequential search. Surprise, surprise. When everything is sequential, it runs the slowest. No real surprise there, right? But what's interesting is that using all parallel isn't necessarily the fastest. So for example, here's everything. Let's see, where's the one? Here's the one where everything is running in parallel. Parallel phrases, parallel searching, parallel docs, parallel works. And you'll see that, of course, it's way faster than the thing where everything is sequential. But ironically, it's not quite as fast as some of the cases where we only do certain things in parallel. Like we look for the works in parallel, and we look for the searches in parallel, and so on. And so the point of this is that you can get too carried away with parallelism to a point where it doesn't really give you a win. Now, the main reason for that in this particular case is just the data that we're looking at. Once you get to a certain degree of parallelism, each of the acts isn't really all that long. And so doing things in parallel is probably not going to give you a win because n is too small to make a difference. But what's cool about this, as you can see, is we try every possible permutation. And in general, the stuff that's parallel runs better than the stuff that's sequential, although there's some subtleties in there. So we'll come back and take a look at that a little bit later. But I just wanted to give you the big picture view of where we're headed. Okay, so let's go ahead and take a look now at search with fork join task. That's the main entry point into this whole thing. And you can see here that search with fork join task takes those parameters. It just stashes them away in various final fields in our search with fork join task class, which itself extends recursive tasks. So that, of course, means it can be run in the fork join framework. And it's parameterized with a list of lists of search results. So what we're getting back from the compute method of recursive task is a list of lists of search results. We'll see how that works in a second. And this is very common with the fork join framework. You typically store things in fields in the constructor, as we do here, all these Boolean parameters and what phrases we're trying to find and what root folder we're looking in and so on. And then all the heavy lifting gets done in the compute method. So if you recall, when the main program calls invoke on the fork join task at the topmost level, that is going to trigger a call to the compute method on that initial recursive task. So at this point, there's one task. The invoke method, as you may recall, is what's called a non-fork join client. So it basically is putting this rootmost, topmost search with fork join task object into the fork join framework. And then from this point, everything goes on in either parallel or sequentially. And we'll take a look at that. So the first thing we do is we get a list of all the folders in the root directory. Now, if you think back to our resources stuff, remember works is where we start. And so these are going to be all the subfolders in the root folder. So, A Midsummer Night's Dream, As You Like It, Henry V, Measure for Measure, Much to Do About Nothing, Julius Caesar, blah, 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 blah. So that's what we're going to do. We're going to get a list of these folders. And then if we're searching the works in parallel, we're going to make a call to the compute parallel method. And then we're going to search those subfolders in parallel using the fork join framework. Otherwise, if we're not doing the works in parallel, we're going to compute everything sequentially. So let's go look at sequential processing first, because it's really easy to understand. So what we do here, remember, this is all Java 7 code. At least this part of the code is Java 7. No fancy streams here, just to keep it old school. And what we do is for each of the subfolders, each folder in the subfolders list, we are going to go ahead and make a call to another object, which we'll look at in a second, called search docs in work task. So what we're doing there is we're going to go look at the various documents that make up a work. That would be things like the metadata file and then all the different acts that we have, Act 1, Act 2, Act 3, and so on. And of course, we pass in the work, which is the folder, or the subfolder. In this case, it would be like Henry V. And then we pass in whether we're searching for phrases and so on in parallel and whatever. We pass in the phrases defined and we pass in various parallelism flags. But what we do here, because we're doing this sequentially, is we don't call fork at all. We just call compute. So that's just a sequential call to compute, which goes ahead and will compute. It'll do whatever search docs and works tasks compute method does. And each of those things get done sequentially. So we do the first work, compute it, add it to the results list, do the next work, so you'd start with a lover's complaint. I don't even know that work of Shakespeare. Next, of Midsummer Night's Dream, next, All's Well That Ends Well, blah, blah, blah. And each of those things is going to be processed one at a time. And so when we're all done, then we'll have a results list of these things called search results, which indicate whether or not there were hits that occurred in that work for the phrases we were looking for. And that will then be returned as a list of search results to then be amalgamated together to a list of search results. So you can see for this sequential version, there is no parallelism going on. We do each work one at a time. Okay, pretty cool, but kind of boring. So let's go take a look at the next example. And this is going to be search with fork join task, except this time we're going to do the parallel version. And as you'll see, it's not a whole lot different from the sequential version. Remember, the sequential version just went through and did compute in the calling thread. This version is just ever so slightly different. We're going to go ahead and create a list of fork join tasks that we all want to run in parallel. And we create a list of results, which is what we had before. The list of fork join tasks is different from the version down here, but the results is the same. And then what we do is we iterate through all the works of Shakespeare And for each work, we're going to call the constructor for search docs and works task, which we'll take a look at in a second. Same parameters. We pass in the work, we pass in the phrases defined, we pass in some Booleans to indicate what's parallel, what's not. But this time, we fork the result. If you recall what fork does, fork arranges to run that fork join task in some worker thread in the fork join pool. It might be the calling threads fork join worker thread. It might be stolen by somebody else. We don't know. We don't care. We just add it to the forks list. And then when we're all done, kind of like what we did last week when we talked about the all iter example, where we just go through the list of forked tasks, the fork join tasks, and for each of these things, we say task.join. And remember that appears to block, doesn't actually block, it just pitches in and processes tasks until it finally gets the one it's waiting for, and then it adds that to the results list. And so we're basically just going to kind of pitch in and help until everybody's been joined. And when we're done, we'll return the lists of search results, much like what we had done down here, except this time, unlike this one where it's all done sequentially by calling compute directly, in this case, we call fork, and then we call join. So I think you'll agree with me that this is fairly straightforward. It's not that much different between the sequential version and the parallel version. But as you can see, even from the simple example we looked at here, when you do parallel works, you get a lot faster performance. So parallel works is pretty much, well, with one exception, this weird anomaly here, parallel works is almost always faster than sequential works. We'd have to look more deeply as to why that is, and it's only off by a tad. But you can see that doing things sequentially, doing the work sequentially is not going to give you a big boost, a big speed up. So parallel works is a good investment. Okay, any questions about that so far? So let's dive in a little bit and take a look at search docs in work task. So here is search docs in work task. This also extends recursive task. We have a list of search results that we're getting back. Remember before, if you go look at this one, we had a list of search results, and now we have a list of search results. And as is our tradition, we have some fields that we define as final fields. We have the work that we're searching, the folder that contains the given work of Shakespeare we're looking at. We have the list of phrases to find in the work, and then we have some Booleans to indicate what we're doing in parallel or not. And I should probably learn to use my plurals correctly, because those should be singular. The constructor just stashes those fields, stashes the parameters into the fields. And as usual, all the fun stuff takes place in the compute method, which of course is overridden from the compute method that's defined in recursive task. So keep in mind, now we're in a given work. So just to be specific here, let's say we're in my favorite Shakespeare play, The Tragedy of Hamlet. And so we're inside the folder for there. So the first thing we're going to do is we're going to get any subfolders there. And there will be one subfolder. It'll be the acts subfolder. So that'll contain the acts of Shakespeare's Hamlet. And then we'll also get any documents that happen to be there. And there will be one document. And the document, of course, will be the list of the participants in this particular play. So now what we do is we say, if the number of folders that we have is greater than 0, we're going to go ahead and take a look at all the documents that are available in that given folder and add them to our documents list. So what we're basically doing here is we're hoisting up all the act files from the acts folder, and we're sticking them in the list of documents. So now we've got, in this particular case, we would have a total of 6 documents, 5 acts, and then one kind of metadata that's the name of the play and the characters and so on. So now we've basically got ourselves a nice list of documents. And what we're going to do is, if we're processing documents in parallel, we're going to call the compute parallel method. Otherwise, we're going to do it sequentially. So again, let's go look at the sequential one first, because it's a little easier to understand. So here's the sequential version. You can see we give it a list of documents, which are basically the contents of that particular work of Shakespeare. And we make ourselves a list of search results, and then we iterate through each document in the work. And we're going to call the constructor for search phrases in doc task. So as you might expect, what that's going to do is it's going to take the phrases defined, and it's going to go look in that particular document to see whether the phrases occur. So again, like it'll look in Act 1 and see if the phrases occur there. It'll look in Act 2, see if the phrases are there. It'll look in Act 3, see if the phrases are there, and so on and so forth. And it'll either do that in parallel or sequentially based on the flags we pass in here. However, for this version, the sequential version, because we're looking for documents sequentially, searching documents sequentially here, we're going to do that sequentially. So we're just going to call the compute method that will block until the computation is done. And then we're going to go ahead and return the results and add them to the results list. So we have a list of search results. So we add all those results there that are returned from compute. And then when we're all done, we have a list of search results coming back. That's the sequential version. Let's go take a look at the parallel version. I think you're going to start detecting a pattern here. So what we're doing here is we now have our list of fork join tasks. We have our list of search results. And this time we're going to do the same thing we did with the sequential version. The only real operative difference being we're going to take each new search phrases in doc task, and we're going to pass the parameters to it, and then we're going to fork it. Once again, arranging to run that particular computation in the common fork join pool, and either in the calling thread or whatever other worker thread happens to steal that particular document. Or that particular document task. So those all get added to the forks array. When we're done forking, we do exactly what we did before. We iterate through the forks array, and we are going to join of each of those things. And we're going to go ahead and add them into the results list, the list of search results. So very, very similar pattern. I think you'd agree. Each time we're doing some things either sequentially, some things in parallel. Every time we do it in parallel, it has a very similar look and feel to it. So let's go take a look at search phrases in doc task. And again, you'll see some very familiar patterns. And let's see, I probably should fix this. It probably wants to be final. There we go. Oh gosh, it's funny. I wrote some of this code a really long time ago, and I wasn't as consistent in my use of final back in those days as I've gotten now. So should make them all final. So search phrases in doc task. So we've got a document, we've got an act, like Act 3 of Hamlet or Act 2 of Julius Caesar or whatnot. And we want to go search for the phrases in that particular document. So we have the title of the document, we have the document itself, we have a list of phrases we're looking for, and we indicate how we want to do the searching in parallel or sequentially. So if you take a look, the compute method is going to return a list of search results. If we're doing things in parallel, we call it compute parallel. If we're doing things sequentially, we call it compute sequential, as is our want. Let's go look at compute sequential. Now things get a little bit different. This is similar in spirit to what we've seen before, but the details differ because we're doing different kinds of computations. So we're going to make ourselves a list of search results, which we initialize with new array list. Of course, if this was using Java 8, we wouldn't have to do this gobbledygook with making new constructors for local variables and so on. We'd use a collector of some kind. And what we do is we say for each phrase in the list of phrases, go ahead and make a new instance of phrase match task. And we'll take a closer look at phrase match task here shortly. And we pass in the contents of the work, we pass in the title, we pass in the phrase we're looking for, and we indicate whether we're going to search for that phrase in that act in parallel or not. But in this case, no matter what this parameter is, we're doing this computation sequentially. So we're going to go ahead and call compute. We're going to get a search result coming back from that, indicating whether that phrase or how many times that phrase was found in that particular document's contents. And if the search results come back empty, we ignore it. Otherwise, we add it to our list of search results. So this is just going to keep chunking through, doing everything sequentially at this level. And when we're done, we have a list of search results that we return as a parameter. Now, if we're doing it in parallel, things are a little different. It's not much different as usual. As usual, we have a forks list. So we have a list of fork join tasks to search results. We have our list of search results. We've always have that. And now we do the same thing. We have a classic Java for each loop. It's been around for a while. And for each phrase in the phrase list, we're going to make a new phrase match task with the title, the contents of the document, the phrase we're looking for, the Boolean. And in this case, because we're doing a parallel computation, we're going to fork. So we create a new fork join task, which once again arranges to run that in the right worker thread. We stick that recursive task, the fork join task, into the forks list. And then when we're done, we iterate through that forks list, joining as we go. And if we get back something that's empty, we ignore it. Otherwise, we add it to the results list. So as you can see, once again, we're doing some pretty canonicalized computations to either do the processing for looking for phrases sequentially or to do the processing looking for phrases in parallel. Well, there's one more piece of the puzzle here, and it's actually, in some sense, the most interesting piece of all. This is the piece called the phrase match task. And this is really, really, really cool. So let's go ahead and take a look and see what the heck we're doing with this. So a phrase match task, of course, is a recursive task, just like everything else we've seen, except it's going to return search results. And it's going to keep track of the document title. It's going to keep track of the input string, which is the contents. So like the text for Act 2 of Hamlet or the text for Act 3 of Macbeth or whatnot. It'll keep track of the phrase we want to search for. It's going to keep track of a regular expression representation of that phrase. And then it's going to keep track of something called a phrase matcher, which is going to bind the regular expression for the phrase to the input that we're searching to see where the matches occur. And then we do a few other things here that we need for the fork join to know when to stop searching. It's called the minimum size of an input string to split. And then we also keep track of the offset. And this is needed so that we know where the actual phrase occurred if we do this in parallel. And then the final thing we keep track of in this field is a flag that indicates whether or not we're doing the match in parallel or if we're doing it sequentially. So this particular code is actually very subtle and very, very cool, but rather tricky to get right. And part of the reason has to do with its very sophisticated use of Java regular expressions, as we'll see. So here's the constructor. We take the title, the input text for the act, the phrase we're looking for, and a Boolean flag to indicate if we're doing things in parallel or not. And we stash the title and the phrase away. And then we go ahead and we do a whole bunch of regular expression magic, which is really cool. We're going to take the phrase and trim off any leading or trailing white space. We're then going to indicate that the phrase starts with a word boundary and ends with a word boundary. And then we go ahead and we replace multiple spaces with a single space, white space boundary expression. And we're going to delimit the words. And this is just to make sure we don't match like substrings. We want to match the phrase exactly. We don't want to match subphrases because there's plenty of subphrases that we could match. And then we go even further and we go ahead and move and modify various punctuations so that they aren't punctuation, if I could spell. I think that might be better. So they're not considered part of a word. We don't want punctuations considered part of a word. We want them to be treated specially. There's just a whole bunch of crazy stuff we have to do to make all this stuff work. And then we compile that particular regular expression phrase that I just set up with those string manipulations to be a regular expression that's going to be case insensitive and will search across lines. So if we have a very long phrase, it'll find matches across lines. Then almost the end here, we go ahead and we say we take the input for the act we're looking at, and we connect that to the pattern, and we end up with a pattern matcher, regular expression matcher. So now we can go ahead and search that input to try to see if there's any matches for that regular expression for that phrase. We then initialize the fields, set the minimum split size, and indicate whether we want to do the search in parallel or not. So that was just the constructor. We're trying to get everything set up so that the phrase matching will be done properly. Here is the constructor for phrase match task. You can see it sets everything up. It takes the input and it matches it with the pattern and sets the other fields. So now let's go ahead and take a look at the compute method. So once again, as usual, we do things either in parallel or sequentially. If we're doing parallel search and the length of the input is bigger than some minimum size, then we're going to do the parallel computation. If we have a very short act with just a few lines in it, there's no sense in doing a parallel search. It takes way more time to set it up than it does any benefit from searching. That's a good example of the n times q formula we've talked about before. If n is very small, we're not going to get a win for parallel computing. So if the input length is short, we're not going to bother with parallelism. In that case, we'll do sequential. So let's take a look at sequential matching. And this is really cool. So what we're going to do is we're going to go ahead and create ourselves a list of search results result objects. So let's go take a look at what this is. Search results is a class that keeps track of how many times a phrase appears in a given input string. And nested inside of the search results class is a class called result that indicates the index where the phrase was found, and also some other stuff that you can use to stringify the object. So basically, this is just keeping track of where the index was found. And there's some other super cool things in there that we'll take a look at later. So then what we do is we say, while we haven't reached the end of our input match, we're going to see if we can find a match. So we go and ask the regular expression matcher, we say, please find me the next match. Now, there may be no match forever at all. So for example, if we look up the phrase, brevity is the soul of wit, in Macbeth, we won't find it because nobody says that in Macbeth. Likewise, if we look up out, damn spot in Hamlet, we won't find that because there is nobody who says that in Hamlet. So it might turn out that when we do the regular expression match, we get back a false, which means there was no match. If you get back a true, however, what we do is we make a new result object and we indicate where the match occurred in the input string. And we keep doing that until we've basically exhausted the entire input string and there's no more regular expression matches to be found, in which case we make ourselves a new search result object, passing in the phrase, the title, and the list of where the matches occur. So that's what compute sequential does. Pretty straightforward. Let's go take a look at compute parallel. Compute parallel is totally over the top in terms of how cool it is. If you had very large input files, which some of Shakespeare's acts aren't very long, some are long, the longer the act file, the more win we're going to get from searching for the phrases in that file in parallel. So let's just for amusement's sake, let's assume we're looking for in a large file for a phrase. So we have a phrase like neither a borrower nor a lender be, and we've got some big honking act with thousands of lines, and we want to go ahead and look it up. So what we do is we take a look at the length of the act of the document we're in, and we divide that by 2, and that tells us where we're going to try to split the input into 2 chunks. And where we're headed with this, just so you keep the big picture in mind, we're going to try to split the input up into chunks. And then we're going to search each of the chunks in parallel. We're going to turn them into tasks, and we're going to go look them up in parallel. So where we're headed with all this is if we can do these things in parallel, we can search through the document faster because we're basically chunking it up into pieces. And then we figure out where the actual split should occur. There's some magic we got to do. I'll explain this in a second, but it might turn out that when we split the document in half, the phrase we're looking for straddles where the split occurred. And if that occurs, we have to adjust the split because you obviously will have no success searching 2 halves of a document that are split in such a way that the phrase you're looking for is cut in such a way that you'll never find a match. So we have to adjust the split. And what we do then is after we've figured out where we're going to do the split, which could either be in the halfway part or some adjusted halfway part, we then call this method called split input, which will then create the tasks that will do this in parallel. So I don't want to get too wrapped up into the details of this. That's very heavily documented code, but you can figure out how this works. We take a shot at trying to do a split just by splitting it in half. That's the start position. And then we call try to update split pause. And that basically checks to see whether or not the split that we did would have been done in such a way where the phrase would have straddled the two chunks. And if it does, it'll adjust it. And there's some super duper cool regular expression stuff in here, which I'm happy to explain if you're curious, but it's really outside the scope of what we're trying to get at. And then finally, once we figured out the split position, we call split input. And this is where we're back now to fork join pool stuff, which is the focus of the conversation. So what we do is once we figure out the split position, we create a new phrase match task, and we give it the subsequence of the input from the beginning up to the split position. And we fork that thing off to arrange it to run in parallel. And then we take from the split position to the end of the input, and we make another subsequence. So now we've got this task, which is the phrase match task. We have this task, which we just updated so that it is going to have its subsequence from the middle to the end. We created another subsequence from the beginning to the middle. And now we've got these two tasks. One of them we forked off. The other one we're just going to compute. So it'll borrow the current worker thread to do this. And after that compute call is done, we'll then join back with the results of the left-hand task, which is probably about done by now because it's working on about half the size. So it does it nice recursively, kind of builds a nice balanced tree of fork join tasks that are going to run in parallel. And when we get the results back, then we go ahead and add the right result to the left result, if there is a right result. And then we return the left result. So we combine the results back together again. So this is basically kind of splitting things up. And we do this recursively, and we keep doing this recursively over and over again until we get to a point where the compute method will detect that the length is greater than the min split size. So it'll keep doing that until we reach a point where it's not worth doing any more parallel processing. So those are all the different ways in which we split things up and chunk them up using the fork join framework. And as you can see, if you just kind of step back here for a second, and again, think of like the big picture view of what we're doing, we are breaking things up in such a way that we're doing the works in parallel, right? So each of the different works of Shakespeare could be done in parallel. For each work, we are potentially doing the documents, the acts, and the metadata file. Those could all be done in parallel. Then within a given document, a given act, or a given file, we're looking for the phrases in parallel. And then for a given act, we can look for a given phrase in parallel. So it's just about as optimized as you possibly can imagine. And when we go over here and take a look at the results, you can see the results. So you can see that for this particular configuration of this particular machine, where I have basically 42 phrase matches that are found in all the works of Shakespeare, you can see that the completely sequential version takes about 3,000 milliseconds to run, and the completely parallel version takes about 415 milliseconds to run. So what that's about, 7.5 times faster, and I've got an 8-core machine. So that gives you a pretty good idea that it's fairly linear speed up, so it's a good example of an embarrassingly parallel task. And that's probably more or less what we'd expect. And then if you take a look at the results here, you can see that the parallel works is really the big heavy hitter. That gives us the best bang for a buck, right? That's where we're saying each work of Shakespeare is done in parallel. That's a big win. You can see that doing the parallel searching, where we actually go ahead and break things up and look for a given phrase in a document in parallel, that actually works pretty well. The phrases being sequential, that they're very similar in terms of time, but basically, as you might expect, that all things being equal, the more stuff we do in parallel, generally the faster, with a few exceptions. And likewise, the fewer things we do in parallel, then the slower, right? But pretty interesting results. And this is a good example of just, trying every possible combination of parallelization using the fork join framework. And of course, in a production system, you probably wouldn't go to this much trouble, but it was just a fun exercise to show you how you can use the fork join framework in a way that can be kind of optimally tuned for the particular characteristics. And I would certainly expect if we used different input, if we were looking up, I don't know, all the works of, trying to think of who was more prolific than Shakespeare. There's not a lot of authors who've written more than Shakespeare. Maybe David Balducci, right? If you took the complete works of David Balducci and you broke them up like this, you might have more works than he'd probably written more books than Shakespeare has, or something like that. But the point is that you would get different results if your input was slightly different. But it gives you a good example of how to use the fork join framework to its fullest extent. Okay, so that's probably more than you ever possibly wanted to know about the fork join framework. The particular thing I like about this example is it took the example that was available on the website. Let's go back to that example. So if we take a look at the example here, it basically takes that general concept and then does something more interesting than looking for a single word, which is what the original example had done. And it also does something more interesting than just looking up a word in documents in recursive folder hierarchy in parallel using the fork join pool. It gives us a much richer way of doing this with regular expressions and n-fold dimensions of parallelism and so on and so forth. But it's still more or less the same kind of idea. So if you read this description, you'll learn kind of the overall philosophy of this with some nice diagrams that kind of illustrate how the fork join framework behaves, which may teach you some insights as far as how that works. But I think my example is more fun. And it's also consistent because I have lots of other examples of searching for things like the works of Shakespeare with other techniques like parallel streams and completable futures and RxJava and all that kind of good stuff. So we may take a look at some of those in future lessons. Okay, so anybody have any questions about any of that?
I have a question.
Sure.
So it makes a lot of sense to me that you have individual works like Troilus and Cressida, Timon, or whatever that are individual. You know that a phrase isn't going to be crossing a boundary there. Same thing with the acts. You can do the same thing there. Once you get inside an act and you're doing your parallel search, now you do have to sort of solve a little bit of the chunking problem.
Right.
And I'm just curious. I don't necessarily. I know it's hard to talk in some like the abstract for some of this, but one naive approach would be I'm going to take every word and then as many words after that as the length of my phrase is, and I'm going to check that, right? And that might work for simple processors kind of a thing. This you're using regex, I assume, on sort of a logically sized chunk because the CPU can kind of handle that. But I'm just kind of curious what considerations go in when the data is not obviously divisible.
Yeah, no, that is a great question. I'm assuming you're asking what if you were doing something along the lines of Google, right, where you're gonna index the world and then search on things. I mean, you'd have to think about. There's so many other things for people who do serious, text searching to think about. This was mostly just because I was having fun learning regular expressions and learning how to break things up and fork join tasks and so on. So I didn't think about it very deeply. But I think if you were going to do this for real, there's undoubtedly much more efficient ways than using the regular expressions package, which is super cool. But it's probably not the most efficient way to do it. There are probably ways to do it where, like you said, you could skip over things if the links weren't appropriate. There's all kinds of optimizations you could put in to make this run a lot faster if you put your mind to it. I was mostly just trying to do it as a teaching tool and teach myself regular expressions, in anger, it's pretty hardcore regular expression stuff, but I was just trying to have fun with that. So I'm sure you could do a much better job if you really needed to do this for real. I should also probably point out that you can get a pretty darn good bang for your buck. I mean, let's go take a look at the results for a second to make sure what I'm about to say is actually supported by evidence to some extent. So clearly the parallel searching is by far the hardest thing to do, right? Everything else, like looking things up by document or by work, by document, by phrase, That's really simple to do, and if you look at the code, it's kind of paint by numbers. It always looks almost identical. And hopefully you got a feeling for the fact that when we did the fork version versus the compute version, there was like an extra line or two and an extra loop, but it wasn't hard and it always looked exactly the same. And so, like I said, it's kind of paint by numbers. Taking a document and then looking for phrases in parallel in the document, that takes some serious doing. That honestly probably took me longer to get that code right than everything else put together. So you have to ask the question, is it worth it, right? So it's actually kind of interesting that it does appear to be worth it here. The fastest version is the one that did parallel works and parallel search. I'm actually quite surprised to see that. I would not have predicted that. And that may, it may just be the trick of the tail, right? Or the trick of the tape. It may just be the way that it happened to run. So we'll try running it again to see if we find a pattern here. But, it's close enough to the other ones that I suspect it might just be in the error noise, right? Let's see. Yeah, so here you go. If you take a look at this one, the next time I ran it, parallel works, parallel docs, parallel phrases was the fastest, and sequential searching didn't really matter, And if you see that time, we got way faster performance too. I have no idea why. It's like the phase of the moon, because this is all a compute-bound process. It's not doing any real I/O once you read it all to memory. So your mileage may vary, but the point is that you can get really good speed ups very quickly by doing kind of coarse-grained parallelism. And then, in practice, I wouldn't go to the trouble of doing the phrase match task unless I could convince myself very confidently that was going to be the thing that got me over the threshold of performance. I probably would stop, once I got like a linear speed up or close to linear speed up, I'd probably just declare victory with what else I've done and say, hey, boss, are we close enough? And they'd probably say, yeah, sure, that's fine. Your linear speed up, not going to do a whole lot better than that. So this is just something you would do if you either wanted to demonstrate it or you were just getting carried away and having fun.
Yeah, it seems like the others are embarrassingly parallel, and then parallel searching can be parallelized if you need it to be, but it's not necessarily as simple as embarrassingly parallel.
Absolutely. That's a great insight. And I think the other way I would look at that is I would really only do the parallel searching if I knew I had large documents to search. If I have a document that has 1 million lines in it, then searching that document for phrases in parallel is probably a win. If I have documents that are, 1,000 lines long or whatever, maybe not so much. It's probably faster just to do it sequentially, or it's easier to do it sequentially, and it may not give you enough of a boost. So yes, your observations are spot on. And that's why it's fun to do classes, because I don't have to sit here and argue with my systems engineers that this is not worth doing. It's just fun. And it taught me some important things. But in real life, I guess the take-home point is go for the embarrassingly parallel first. And if that doesn't get you far enough, rethink whether you need to go further. And also, as we've talked about before, I'm showing you this stuff because I want you to understand how fork join works. And if you were ever on a project where you were doing Java and you couldn't use modern Java, you were stuck in a time machine in 2013 or something like that, like Groundhog's Day, and you can only use Java 7, well, you can still get a big boost in performance. But honestly, if you were doing this for real, I would probably recommend using parallel streams, which would be way easier and probably perform about the same. This also, though, is an interesting example, and we'll get a closer look at that maybe next week. This example is one of those things that it may not actually be a big win to use a parallel stream for this in a lot of ways, because the way in which the directories are organized doesn't necessarily give you that split evenly thing. Again, you can split the works evenly. That would work well with a parallel stream. Arguably, you could split the documents within a work evenly. You could split the phrases evenly, but it might or might not be as big of a win just because of the way that parallel streams wants to kind of have everything be equal. So parallel streams works better if you have a top level data source that can be split up into small chunks down to atomic size small chunks, and that's it. Whereas here you can see we have like recursive nesting of things. So parallel streams might or might not be a win. And in fact, I have a whole other set of things we could look at that demonstrate that too. But that's another topic for another time. Okay, any other questions? That was a great question. So I think I don't really have anything else to cover. I figured that was more than enough for tonight, was to go through 45 minutes of fork join stuff, a little longer than my typical examples. I haven't actually presented that particular example live. I don't know if I ever did it live. It's just a cool example I did a while back, but it was kind of fun and it fit with the themes that we're talking about for this section of the course. What you can do this week, obviously, is finish off the fork join example. Hopefully the new tests are working. I haven't heard any complaints about the tests, so hopefully we got the tests working better, and hopefully the repository is working better. Again, I apologize for the hiccups there, but please let me know if you have any questions. Happy to take questions now. If you want to come to office hours tomorrow, that's fine too. If you have any other questions, please don't hesitate to post them on Piazza. Great. Well, then, without objection, hope you have a good rest of your night. We have about 15 minutes left, but that's okay. I'm sure you can find a profitable way to spend the rest of your evening. And I will look forward to talking to you soon.
Thanks. Bye.
See ya.
Bye.
Thank you, Professor.
Thank you.